So there is no loss of kinetic energy, and of course momentum will be conserved. We'll look at it later. But then the main point here is the coefficient of restitution is 1 for perfectly elastic collisions. Now let's look at another scenario and try and understand what is inelastic collision. Let's say there's an object A, moving towards object B, and then after the collision they stick to each other. Let's assume they are made of something like made of glue or some sticky material, so that like a dough. So after hitting each other they tend to stick to each other and then continue to move, but then both together become one mass. So this is a perfectly inelastic collision where there is no perfect bounce back like what we saw in the case 1. They stick to each other and become one mass. In such cases, the relative velocity, the coefficient of restitution, or the relative velocity after the collision, and relative velocity of A with respect to B after by relative velocity of A with respect to B before collision. If it is perfectly inelastic, what does it mean? Sometimes it's not perfectly inelastic, in which case they will continue to move in this direction or that direction. But if it's perfectly inelastic, it means there is no bounce at all. They don't bounce away from each other at all, and then they stick to each other and come to rest. Then it will be zero. The relative velocity of A with respect to B after collision will become zero if they come to rest. It is like something gluey thrown on a wall and it sticks to the wall. Then it's perfectly inelastic. But typically it's not perfectly inelastic. There are cases where E lies between 0 and 1. So in this case, the coefficient of restitution is a number between 0 and 1. They hit each other, but they don't bounce back completely. There is some loss of kinetic energy and there is something getting deformed. Then the velocities change after collision. But if we calculate the relative velocities after collision, then the relative velocity after by before will be typically something less than 1. This would be lesser. The numerator would be lesser than the denominator. Relative velocity of A with respect to B would reduce typically. But if it totally comes to a halt and they stick together and stay there, then it is called perfectly inelastic. That means this numerator becomes 0. Then it's perfectly inelastic. But the most important thing in both these cases is there is a difference between elastic and inelastic collisions. In the first case of elastic collisions, momentum, linear momentum, which is represented by P, is conserved. I'll explain that more later. And in this case, momentum is conserved. Momentum, by momentum I mean the momentum of the system. A and B together are the system, and there is no external impulse or force acting on them. That is the condition here. Same as the second scenario. A and B are part of the system, then there is no other external force or impulse acting on the system. In such cases, the momentum in both cases is conserved. That means the momentum before collision will be equal to the momentum after collision. Momentum initial before collision is equal to momentum final, which is after collision. Same is the case for inelastic collisions also. But there is something that changes between these two scenarios, which is kinetic energy. So kinetic energy in this case is conserved. In elastic collisions, it is conserved. But in the second case of inelastic collisions, kinetic energy initial not equal to kinetic energy final. It is not conserved. Here it is conserved. Kinetic energy initial will be equal to kinetic energy final in the first case. In case number 2, kinetic energy is not conserved.